Hello students, I am Dr. Navneet Kaur, Associate Professor in Department of Electronics and Communication Engineering, Sagar Institute of Research and Technology College. Today I am taking third lecture of subject Digital Signal Processing. In my previous lecture, I had discussed about classification of the signals. In this lecture, I'll continue with the classification of signals and I'll discuss different types of signals and their properties in detail. We had already talked about even and odd signal. A signal is said to be even or a symmetric signal if it satisfies the condition of symmetry, which is x of n is equal to x of minus n. Whereas a signal is said to be asymmetric, antisymmetric or odd signal when it satisfies the property x of minus n is equal to minus of xn. Any signal xn is made up of even and odd component. Now suppose if we are given any signal and we are asked to find out its even and odd component, then we can find out by using the formula xen, which is even component. It is given by x of n plus x of minus n divided by 2, where x of minus n is the folded version of the signal xn. And xon, which is odd component, is given by x of n minus x of minus n divided by 2. Now we will derive the formula for even component xen and odd component xon. Now we are given signal xn, which is xen plus xon. We will put n is equal to minus n here. Now when we put n is equal to minus n, we will get x of minus n is equal to xe of minus n plus xo of minus n. Now we know from the definition of the even and odd signal that xe of minus n is equal to xen, whereas xo of minus n is equal to minus xon. So here from equation 4, we will get x of minus n is equal to xe of n minus x naught of n. Now we will add equation 4 and equation 7. Now, when we will add these two equations, we will have odd component which will be opposite in sign. So this odd component will get cancelled and we will get x of n plus x of minus n, which is equal to 2xen. So xen will get x of n plus x of minus n divided by 2. Similarly, we will subtract equation 7 from equation 3. Here, the even component will get cancelled and we will get x of n minus x of minus n, which is equal to 2xon. So xon will be half xn minus x of minus n divided by 2. So this is how we can find out even component and odd component of any given signal. We will take the signal xn and find out its folded version x of minus n. We will sum it up and divide by 2. We will get even component. We will subtract the 2 and divide by 2. We will get the odd component. Now coming to the periodicity of a signal. We had already talked in the previous lecture that any signal is called a periodic signal when it satisfies the property x of n is equal to x of n plus n. This means that the signal repeats itself after a fundamental period capital N. So this capital N is the number of the samples after which the pattern of the signal repeats itself. So capital N is known as the fundamental period. Now, here we will find out the condition for the periodicity. Now we have already discussed that for signal to be periodic, x of n should be equal to x of n plus n. Now, for example, we will consider xn as any sinusoid signal, which is given by a cos 2 pi f naught n plus theta. Here, A is the amplitude of the signal, theta is the phase shift, F naught is the frequency. Now, according to this equation, if I'll put n is equal to n plus n, we will get A cos 2 pi f naught. Here in place of n, I'll put n plus theta. Now, since the signal has to be periodic, it must satisfy this property. So, for x of n plus n, I'll put this expression, and xn I already know it is a cos 2 pi f naught n plus theta. Now, these two sides of the equation should be equal. Now, for these two sides to be equal, the condition is that that 2 pi f naught, this part is extra in these two sides. This 2 pi f naught n should be equal to 2 pi k, where k is any integer. Now we know that if it is k is 0, it will be 0. So in that case, the two sides are equal. Now, when we have 2 pi f naught n is equal to 2 pi, when k is equal to 1, then in that case, cos of 2 pi plus theta, we already know it is equal to cos of theta. So when we put k is equal to 2, we will get 4 pi. So cos 4 pi plus theta will be again cos theta. So for this condition to exist, we should have 2 pi f naught n is equal to 2 pi k, where k is any integer. Now 2 pi or 2 pi will get cancelled. So f naught will be given by k upon n, where k is any integer and n is the fundamental period, which is also an integer. So f naught should be the ratio of two integers. That means f naught should be a rational number. So any discrete time sinusoidal signal is periodic when its frequency f naught is a rational. That means f naught should be expressed as the ratio of the two integers, and the denominator of f naught will give the fundamental period of that periodic signal. Now, next we'll discuss about basic operations on the discrete time signal. Now, the first operation which we will discuss here, it is time shifting operation. Now, time shifting operation is carried out in two ways. First is the time delay. Now, suppose I have any signal xn and I want to generate another signal yn, which is equal to x of n minus k, where k is a positive integer. We will call yn is the delayed version of the signal xn. Now we will explain it with the help of an example. Now suppose I have xn, which is equal to 1, 2, 3, 4, 5. It is represented by this sequence. Now this arrow, it is representing sample 1. Arrow means we are considering for n is equal to 0. That means 1 means that the sample is at n is equal to 0. Similarly, 2 means that the sample is at n is equal to 1. 3 means that the sample is at n is equal to 2. 4 means n is equal to 3, and so on. Now, if I want to generate another signal which is given as x of n minus 2, that means here the value of k is equal to 2. That means that I am delaying this signal xn by 2 samples. In that case, the whole sequence will be shifted to right by 2 samples. That means that the sample 1, which is located at n is equal to 0, now it will be located at n is equal to 2. Similarly, the sample 2, which is located at n is equal to 1, now it will be located as n is equal to 3. Now for 1, we will have sample 0, because the sample which was at n is equal to -1 is now shifted to n is equal to 1. Since we had no sample, that means we had sample 0 at n is equal to -1. So we will get now 0 at n is equal to 1. Now similarly, the sample which was located at n is equal to -2 is now shifted to n is equal to 0, which is sample 0. Now, this is the graphical version of the signal x of n minus 2. Now say this is signal xn, which is having x-axis as n. Now since we have 1, 2, 3, 4, 5, so at n is equal to 0, I'll get 1. At n is equal to 1, I'll get 2. At n is equal to 2, 3, and so on. Now after delaying it by 2 samples, I'll get at n is equal to 0 and 1, 0, 0. And now my sequence will start from n is equal to 2. At n is equal to 2, I'll get sample 1. At n is equal to 3, I'll get sample 2, and so on. Now, coming to the next time shifting operation, which is time advance. Time advance means that I will have new signal which will be represented as xn plus k, where k is any integer. Say I have k is equal to 2. Now here I want to generate a new signal which is xn plus 2. Now originally I have sequence xn which is 1, 2, 3, 4, 5. Now when I generate xn plus 2, that means the whole sequence will be advanced by 2 units. That means the whole sequence will be shifted towards left by 2 samples. That means the sample which was located at n is equal to 0, now it will be shifted to n is equal to -2. So now we can see at n is equal to -2, we have sample 1. Similarly, the sample which was at n is equal to 1, now it will be shifted to n is equal to -1. So here at n is equal to -1, we will have sample 2. Similarly, at 0, we have 3. Then at 1, we have 4, and so on. This is how we will get a time advance signal of any signal. Now, next we have folding of the signal or time reversal of the signal. I had already told you when we were discussing about even and odd component of the signal that the folded version is represented by x of -n. Say we have any signal x of n, which is 1, 2, 3, 4, 5. Now in the signal, no arrow is shown here. That means by default, the sample 1 is located at n is equal to 0. That means the arrow is located at sample 1. So this is at n is equal to 0, this is at n is equal to 1, then 2, then 3, and 4. Now, for folded version means that I'll get a mirror image of the signal. That means whatever the samples are located on the right hand side of the y-axis, now they will be shown on the left hand side. And whatever the samples which are on the left-hand side of the y-axis, they will be shown on the right-hand side. That means all these samples which are located at n is equal to 1, 2, 3, and 4, now they will be located at -1, -2, -3, and -4. And the sample which was at n is equal to 0, it will remain at n is equal to 0. Now this is called the folded or time reversal signal. Now, next we will do the combination of the two operations. That means when we are delaying as well as folding a same signal. In that case, we will get two operations on the same signal, that means delaying and folding. Now say I have a signal xn. Now first I'll delay it by say k samples, which will be given as x of n minus k. Now I'll fold the signal. So after folding, x of n minus k will be given as x of minus of n minus k, which will be given as x of minus n plus k. That means x of minus n plus k, that means I'll fold the signal. Then I will advance it by k samples. Now, this is x of minus n plus 2. After folding, if I'll advance it by 2 samples, in that case, my sequence will be shifted by 2 units towards right. Remember that in normal sequence xn, when we advance the sequence by 2 samples, that means we are shifting my sequence towards left by 2 samples. But since we have folded the sequence originally, in that case, after folding, if I want to advance the sequence by 2 units, in that case, I'll have to do the reverse operation. Instead of shifting the sequence left by 2 units, I'll shift it by towards right by 2 units. That means after folding, advance means moving towards right. And after folding, delay means moving towards left. So when I'll move the sequence by 2 units towards right, in that case, my sample 1 will move to n is equal to 2, 2 will move to n is equal to 1, and sample 3 will be at n is equal to 0. That's why the arrow is shown at n is equal to 3, and 4 will be at n is equal to minus 1, and sample 5 will be at n is equal to minus 2. Now, this is how we have shown the folding and the shifting operation graphically. Now, this is the folded sequence, which is having n is equal to 0, 1, n is equal to minus 1, 2, and so on. After advancing it by 2 units, I'll shift it towards right by 2 units. So my sequence will be shown like this. Now, the next operation is the time scaling operation. Now, say I have any sequence xn and I want to generate another sequence yn is equal to x of 2n. Now, in that case, what I'll get, I will have a time scaled signal which is given by x of 2n. Now, say if I put n is equal to 0, I'll get x of 0 as y of 0. But when I'll put n is equal to 1, that means y of 1 is equal to x of 2. That means whatever the sample which was located at n is equal to 2 in case of xn, now it will be located at y of 1. That means it will be located at n is equal to 1 for y. Similarly, if I'll put n is equal to 2, I'll get x of 4. That means y2 is equal to x of 4. Similarly, y3 will be at x of 6. Now, if I'll draw the sequence, as I already told you, y0 is equal to x of 0, which will be 1. y1 is x of 2, which is 3. y2 is x of 4, which is 5, and so on. So I'll get 1, 3, and 5. That means in between the samples 2, 4, they are lost here. So here we are increasing the sampling interval. That means if we are increasing the sampling interval, the frequency is reduced. So that's why it is known as downsampling, because here the sampling frequency is reduced. Now, next example of time scaling we will see as yn is equal to x of n by 2. Say, for example, I have any sequence xn, which is 1, 2, 3, 4, 5, and sample 1 is located at n is equal to 0. Now, if I want to generate y of n, I'll put n is equal to 0, which will be x of 0, which is 1. Now, if I want to get y of 1, it will be x of 1 by 2. We already know that the discrete time signal is always defined at integer values. So x of half is having no value. So there will be no sample at y of 1. Now y of 2 will be x of 2 upon 2, which is x1, which is 2. Similarly, at y of 3, it will have no sample. At y of 4, it will be x2, which is 3. And y of 5, it will have no sample. Similarly, y of 6, it will be 4. At y of 7, we'll have no sample. At y8, we'll have x of 4, which is 5. And at y of at y of 9, we'll have no sample. So yn will be given as 1, 0, 2, 0, 3, 0, 4, 0, and 5. That means here the sampling interval is reduced because between the two samples 1 and 2, I am taking one more sample, which is 0. So here the sampling interval is reduced. That means we are increasing the sampling rate. That's why this operation is also known as upsampling. So this is the sequence yn, which is xn by 2, which is 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. So this operation is known as upsampling because in this case, the sampling rate is increased. Now, this is all for today's lecture. Thank you.